A dark ocean, billions of years ago. A universe where there was only hydrogen and helium. No stars, no galaxies, no structure. Just energy and silence. Then, gravity started playing. And from that was born the story we call galaxy formation. Today we are about to understand how galaxies formed, how an unseen substance we call dark matter laid the foundation, how gas condensed to form the first stars, how the explosions of those stars created new elements and new worlds. It's a journey from the shadow of dark matter to the light of glowing galaxies. And new data is shaking up our old models. First, understand the framework. Dark matter halos formed first. These are gravitational traps that pull on gas. Gas accumulates in these halos, cools, and spins into a disk due to angular momentum. This is where star formation occurs, when dense clouds of gas collapse under pressure and new stars are born. But this process is not uncontrolled. Supernova explosions, radiation, and stellar winds provide feedback, which keeps new star formation regulated. Without this feedback, all the gas would turn into stars at once, and galaxies would disappear in a momentary flash of light. Galaxies grow through mergers, when two or more galaxies collide to form a larger galaxy. Sometimes these collisions are violent, sometimes calm. This process gives rise to spiral, elliptical, and irregular shapes. This continuity is supported by our Lambda-CDM cosmological simulations. But now the data is saying, the story is not so straightforward. Let's go back in time, when the universe was only 300 or 400 million years old. This was when the first galaxies were emerging. The James Webb Space Telescope, JWST, showed us a view that had never been possible before. It saw a galaxy called JADE's GSZ 13-1, which existed just 330 million years after the Big Bang, and where the Lyman alpha emission line was clearly visible. This signal suggests that the hazy veil of the early universe, the neutral hydrogen known as the reionization era, had by then cleared up considerably. And then came the discovery of MOM-Z14, another galaxy, perhaps only 280 million years after the Big Bang. The discovery was confirmed by NASA, and it was like a slap in the face to our theoretical models. Because by our calculations, such a mature galaxy was impossible at such an early time. Then came more shocks. A galaxy called J0107A, which has a structure exactly like our Milky Way, but 10 times more massive and is producing stars 300 times faster. When the universe was only 2 billion years old, this galaxy had already become a giant. Another example. JWST discovered about 300 bright early cosmic objects that, according to theory, could not have been so bright. Some scientists said, maybe these are not galaxies, but rather exotic phenomena. And then, a dead galaxy was found, which had stopped producing stars after only 700 million years, with a mass equivalent to 15 billion suns. That is, an old galaxy existed in the infancy of the universe. Now the question is, how did it all happen so quickly? Was physics hiding something? First answer, efficient cooling and early metal enrichment. The first supernova explosions produced heavy elements, carbon, oxygen, iron, which cooled the gas quickly, accelerating star formation. Second, high gas fraction and turbulence. The early universe was gas-rich, dense, and had strong gravitational interactions. All of this fueled starburst activity. The third possibility: direct collapse black holes and AGN feedback. The massive black holes at the centers of some early galaxies formed directly from stellar collapse, without any stellar growth. They regulated the growth of galaxies by releasing gravitational energy. JWST has discovered a similar unique black hole in the Infinity Galaxy, whose origin is still a mystery. Fourth, some physicists are investigating alternative properties of dark matter. If dark matter were slightly warmer or self-interacting, structure formation would be possible much more quickly. This is still speculative, but mathematically plausible. Fifth mechanism: mergers and accretion channels. Galaxies were merging rapidly in the early universe in overdense regions, which we call proto-clusters. But not every large early galaxy was the result of a merger. Some grew up more quietly, like the case of J0107A. So what does this mean? Simple. We'll have to rewrite our cosmological models. Star formation efficiency. Feedback strength. Initial mass function. All have been called into question. Simulations like Illustris, Eagle, and TNG will need to be recalibrated for the early ages. There's still work to be done on the observational front, too. JWST and ALMA have given us visual clues. But now, spectroscopic confirmation is needed, so that we can determine the precise distances and chemical compositions of these galaxies. The upcoming Nancy Grace Roman Space Telescope and the extremely large telescope will add to this data set. This is not just science, it is philosophy. We used to think that the universe was slow and predictable. Now we know. The universe was racing. In its first billion years, it created structures that we thought were impossible. This fact shows us that nature never stops, but rather pushes its limits. Today we are seeing images from the earliest days of the universe. And each image, each data point, tells us a new story. The story is not that we understand it, but that we still have a lot to learn. Every galaxy is a chapter, every star a word, and every photon a message.